Hi, this is lecture 3 of Instructor 3, lecture 3 of Instructor 3. So, in last two sessions what we have seen is the order structure on R, the field structure on R and the order structure on R. So, R, I am not writing all the other details of the field structure. So, R is a field here and there is an order S on R that is compatible with the field structure on R. So, this was the two layer description of R. Then we have asked that this order satisfies completeness property. So, what does this mean? This is where we have stopped in the previous session. We just mentioned about this completeness property and we didn't really explain what this really means. So now we will just recall what we have already said and we will try to understand what it really means. So, the property is the following: if I take two subsets of R with the following description, with the following property, what is it? If I take an element of A, an element of B, this should satisfy this property A less than or equal to B. If this is the situation, if this is the case, then the completeness property says there is an element S belongs to R such that every element of A is less than or equal to S. Every element of A is less than or equal to S. At the same time, every element of B is greater than or equal to S. This is for every A belongs to A, this is for every B belongs to B. So, this is the completeness property of the order. Maybe I will say one more time. So, what does this property says? If there are two subsets of R, A and B, subsets of R with the following condition, that for if I take any element in A, any element in B, they should be related in this way. Every element of A should be less than or equal to every element of B. Then there is an element in R such that that element S is greater than A for every element of A. It is less than or equal to B for every element B of B. So, this is the completeness property of the order, completeness property of order. Right. So, with this completeness property, we will try to understand more about the set of real numbers. So, if you can recall what we have said in the introduction is, first part of study that we are planning to do on the set of real numbers in this course of real analysis is that we are trying to work with, we are trying to understand power set of R, subsets of R. That's what we said in the introduction. So, we are trying to understand this set. This is set of all subsets of R. This is the usual notation for set of all subsets of R. So, we want to understand what this, we want to understand about this set. Now, we will try to use this completeness property to understand this, but unfortunately this completeness property is not true for any, I mean this kind of existence or any extra information is given not for any arbitrary subset. They have to be of this form. So, this suggests that maybe we should work with a restricted subset of PR, not the whole PR, because we do not really know about any two arbitrary elements here. So, this is what I will write down. So, this is what we are going to focus on for some time, and this is denoted by BR, set of all bounded subsets of R. So, I will explain what this really is. So, a subset of R is said to be bounded above if there is an element M belongs to R such that M is greater than or equal to A for every A belongs to A. In that case, we say that A is bounded above and M to be an upper bound of A. Similarly, one can define about bounded below case. A belongs to R, we say it is bounded below if there is element M belongs to R such that M is less than or equal to A for every A belongs to A. If this is the case, if I am able to find an element M belongs to R with this property, then A is said to be bounded below and this M we will call it to be a lower bound of A. Now, I mentioned about bounded subsets, but here I am saying bounded above, bounded below. A subset is said to be bounded if it is both bounded above and bounded below. Before we see some examples, let us try to understand, let us try to use this completeness property to say something about this kind of sets. So, let us take an element, a subset of R that is bounded above, say. Now, so now what do we have? There is some element M belongs to R such that A is less than or equal to M for every A belongs to A. See, this M is not unique in the sense, this is capital M. See, this M is not unique in the sense, if I take any other element, say M prime belongs to R with M less than or equal to M prime, we of course have this property, right? Transitivity of the order says A less than or equal to M prime. This is also for every A belongs to A. So, this notion of upper bound is not unique. So, for every element M prime that is greater than M, we have this property. So, now what we do is we collect all such upper bounds. So, let me write down in subset B. B is M belongs to R such that A is less than or equal to M for every A belongs to A. This is the set that I am considering now, and I know this is non-empty because it is already mentioned that A is bounded above. So, there will be some element M with this property. So, what I am doing, I am collecting all such elements. So, I am just considering all such elements. Now, think about the relation between A and B. If I take an element A belongs to A and element M belongs to B, what do we have? By definition, M is such that for every A we have this property. So, A is less than or equal to M. So, this says the sets B and A satisfies this condition. So, now we can apply this completeness property of the order and then say there is an element S belongs to R with this property. So, let me write down that. So, what does this say? There is an element S belongs to R such that S is greater than or equal to A for every A belongs to A. Similarly, S is less than or equal to M for every M belongs to B. Now, we need to make some observation here. It is possible that there may be two elements of satisfying this condition, right. So, let us take say S and T belongs to R such that A is less than or equal to S and T less than or equal to not T again S less than or equal to M for every A belongs to A and M belongs to B. I can write down the same thing, just copy pasting. I can write down the same thing for T here, right. T is also of the has same property. Let us assume that there may be two elements. Now, see this T is also an element of B because this is what we have. So, in particular this is less than or equal to, right. So, what I said just now, for every m belongs to B, S is less than or equal to M. In particular, T is also an element of B. So, this is what we have. Now, I think you know now what I am going to do. For the second thing, A less than or equal to T, T less than or equal to M, this is for every m belongs to B. In particular, S is also an element of B, because that is the definition of B, right? A set of all elements which are less than or equal to A for every A belongs to A. So, this S in place of M I can just write down S here, right. So, now what do we have? We have S less than or equal to T and T less than or equal to S. So, this should tell you that S is equal to T. So, we are starting with a description that a subset of A is bounded above, then we got a unique element satisfying this property. Let us rewrite that. So, A subset of R is bounded above, then there is a unique element S belongs to R such that first of all what do we have? It is an upper bound, right, that is a description, that is an element of B. So, it is an upper bound. So, A less than or equal to S for every A belongs to A, that is the first condition. What is the second condition? S satisfies this property for every m belongs to B. What is the element in B? It is an upper bound. So, S is less than or equal to any upper bound. So, let me write down that S is less than or equal to T for every upper bound T of A. So, such S is called supremum of A, right. We have, maybe I should write the supremum, because we have proved that there is for if two elements satisfies this property, they have to be equal. That is what we have done here, right. So, we took two elements of R satisfying these two properties, that is what I mentioned here. This concludes that S is equal to T. So, for a bounded above for a set which is bounded above in R, there is a unique element S belongs to R such that it is an upper bound first of all. Secondly, for any other upper bound T, S is less than or equal to that. So, this is what the notion of supremum of a subset of bounded above subset of A, subset of R is. Now, one can do the same thing for bounded below. So, let us take a bounded below subset. See, one can again do the same thing that whatever we have done before. Now, instead of collecting all upper bounds, let us collect all lower bounds, right. It is bounded below, so there will be some lower bound. So, let us collect all lower bounds. B is equal to M belongs to R such that M is a lower bound. Now, the same justification, not even a single change. What does it say? It says for every B belongs to B and A belongs to A, we have B less than or equal to A. Again, it says there is an element S belongs to R such that B is less than or equal to S for every B belongs to B and S is less than or equal to A for every A belongs to A. See, just remember we are starting with A. Remember we are starting with A. So what is, and again the same previous justification says such S has to be unique. We call such S to be infimum of A. So, what is infimum of A? First of all, it should satisfy this property. What is this? It is a lower bound. S is a lower bound for A. For every element A belongs to A, we have S less than or equal to A. That is what we said as lower bound, right? Did we say that about lower bound, upper bound? Yeah, we have mentioned here. So, M we said it is lower bound of A. So, here we are saying S is the lower bound of A. So, for every element A belongs to A, we have this property, so S is the lower bound of that. Then for any other, see what is B? B is collection of all lower bounds. So the first condition says for any lower bound of B, S is greater than that. So these are the two conditions that defines the notion of infimum of a bounded below subset of A. So maybe I should just write one more time. So let me denote set of all bounded below subsets by this, set of all bounded above subsets of R by this. So these are all, these two are subsets of power set of R. Now what do we have? We have a map from bounded below subsets to R, bounded above subsets to R. This we are calling as, for bounded below, what do we have? If it is bounded below, there is a lower bound, then we are considering all lower bounds, then there is a maximum element. We should not use this word. There is element that is described by these two, set of all lower bounds and the set A, that we are calling as infimum. So this is the shorthand notation for infimum. I should write INF, I should write the full thing, but I am simply writing infimum. Inf for infimum. Similarly, if I take any bounded above subset of R, what I did is I collected all upper bounds of the set A, then we realized for any two elements, for any element A belongs to A and B belongs to B, A less than or equal to B, then we proved the completeness property of the order suggests an element S belongs to R with some property. What is it? First of all, it's a upper bound of the set A. Then for any other upper bound, we have this inequality, S is less than or equal to that upper bound. So that we have called as supremum. So completeness property of the order is giving these two maps. So maybe we will learn something more about these two maps. Let us ask the following question. In case of, if I am starting with the order structure and the field structure, using field structure what I have seen is there are some elements, the field structure of R comes with only two elements to start with, 0 and 1. Then the addition multiplication properties, using these two maps and the additive inverse and multiplicative inverse, we have produced three sets. One is natural numbers, one is integers, one is rational numbers. Then using order compatibility, we didn't really do anything, we didn't use it to prove anything. Maybe I will try to write down this order compatibility. It looks like it is controlling something, I mean it is forcing something to not happen. Let me clarify what I really mean. So S is an order on R. So the compatibility between this order and the field structure is forcing something to not happen. For example, one can ask the following question. Suppose there is an element A belongs to R such that 0 is greater than A. Maybe I should write down A less than 0. Suppose A is less than 0, can I think of existence of some element in R, is an element S belongs to R such that S dot S, which we are writing as S square, can it be equal to A? Right, one can ask this kind of question. For A negative, can I produce an element S belongs to R such that S square is equal to A? Now this order condition, it is stopping this kind of things to happen. Let me explain what I really mean. So if A is less than 0, okay, maybe one easy way to see is the following. See, there are two possibilities for this, right? Either S is positive or S is negative. If S is equal to 0, 0 dot 0 is 0, so that option is gone. So either S is positive or S is negative, right? Suppose S is positive, what is order compatibility says? If I multiply a positive element on the both sides of an order, the inequality should not change. So if I multiply S on both sides, this should not change. So what does this say? This implies S square is positive. So this option is gone because S square is equal to A and A is negative. So this option is gone. Now see this is still there, this might still work, we do not know, right. So let us try that. So if S is negative, I will simply consider minus S, minus S is positive, right. Now I can apply minuses, I can multiply minuses on the both sides of this order and the order still does not change, right. Minus S dot minus S is greater than 0 dot minus S, but this is 0 anyways, so maybe we can just remove this, simply write 0. And what is minus S? Minus times minus, we have seen in the previous session, maybe as an exercise, that minus times minus is 1. So this is same thing as S square. So here also we are facing the same issue. So even if S is positive or S is negative, the square is always positive. So there is no way for a negative element to have this situation. So this is in some sense stopping something to happen in R. There cannot be an element of R whose square is negative. So this is, yeah, this is first, this may be some observation. Yeah, this might be useful to really understand whether order is suggesting some free nature in the set of real numbers R. So this R cannot have this kind of elements. Now one can ask, okay, what about A positive? Right, for A negative, yes, this is not there. For A positive, do we have anything like that? That we will see soon, maybe in a couple of minutes. Now, so again we will come back to the following question. Existence of order is stopping something to happen. It is stopping this kind of things to happen. If it is negative, this kind of things cannot happen. So in that sense, it is restricting it is saying some questions do not have any answer. That's what is right. So this kind of things cannot happen. Now the question is the following: what does completeness of this, right, what is completeness property of the order? What is it useful for? One thing to observe is, this is the first time we said there is some element in R. In the description of real numbers, we only said, there we have said about existence of two elements, 0 and 1, right. Then in order we did not say anything about existence. Then again here we are saying again there is some element S belongs to R with certain property. So this gives us some hope that R might have more elements than NZQ. Let us see what do we have. We are looking for some proof that says R has more elements than natural numbers, integers and rational numbers. So maybe let us try to answer the previous question that we asked. Suppose somebody tells me that there is a, okay, the question is the following. Let us take 2 belongs to R, 2 is positive, for 2 negative, I mean for negative numbers the previous question says there is no answer. So let us take 2 to be, let us take a positive number, maybe 2. Now the question is, can I think of an element A belongs to R such that A square is equal to 2? See, if I am starting A to be negative, then this possibility, if I am starting with some negative number, there is no element in R whose square is that option is gone. So maybe I will start with the positive element, 2 is positive. The question is simple question, can I think of an element in R whose square is 2? That is the following question. Now we will try to use the completeness property of R and try to answer this to some extent. So consider the following set. So the set is the following: set of all elements A belongs to R and positive such that A square is less than 2. Similarly, B is such that elements of positive real number P square is greater than 2. So now we were trying to use the completeness property. So first thing to check is, if somebody tells me A is an element of A and B is an element of B, do I always know that A is less than or equal to B? In the sense, so what does this say? This says A square is less than 2. can put equality, remove the equality, it's okay. So a square is less than 2. So what does this says? B belongs to B. This says 2 is less than or equal to B square. So once we combine this using transitivity property, this says A square is less than or equal to B square. Now because A and B are positive numbers, this implies this. Maybe we will see, I will give this as an exercise, you will see some. So this is easy to prove, but it still needs a proof. If A and B are positive numbers, then A square is less than or equal to B square implies A less than or equal to B. So these two subsets, one can apply completeness property of whatever I mentioned in the beginning of this session. One can apply completeness property for these two sets, because we have this condition. If I take any element in A and element in B, we have this A less than or equal to B. So what does this say? This says there is an element S belongs to R such that A is less than or equal to S for every A belongs to A, and S is less than or equal to B for every B belongs to B. Right? Just remember, what are we trying to do? We are trying to look for an element in R. I am writing using A here, so let me use some other element, say T. So we are looking for an element in R whose square is 2, but completeness property says there is some element, right? Maybe this is the element that we are looking for. We don't know. How do we know? Unless we check that the square is 2, we will not be able to make sure about whether this is same thing as what you are asking. So let us check. A square, is it, here we are writing as A square, is it same thing as 2? Now this is an element of R, A square is also an element of R. Now the total order nature of the total order property says what? For any two elements A and B, exactly one of the following occurs, either A equal to B or A less than B or A greater than B, either this or this or this. Suppose, see, think of A as A square and B as 2. So one of the following conditions should occur, either A square is equal to 2 or A square is less than 2 or A square is greater than 2. If A square is equal to 2, then there is nothing really, we do not really have anything to do, and we are very happy. If A square is not equal to 2, then there are other two conditions, right? So we have to get rid of this situation. So assuming A square is less than 2, we will try to proceed further to some extent, then hoping that we will get some contradiction. That is the basic idea. Similarly, A square is greater than 2, we will start with this assumption and try to get some contradiction. Then these two will not occur, then this is the only possibility. So, and that says for 2 there is an element S belongs to R positive whose square is 2. Now let us assume that S square is less than 2. Then what happens? Just remember the property of S. What is S? S is such that S is less than or equal to B for every B in B. What is this? An element of B has a condition that B square is greater than or equal to 2, right? Similarly, S is greater than A for every A belongs to A. What is this? A square is less than or equal to 2. Now starting with this condition, let us try to arrive at some contradiction. Now there are two choices, either I need to produce an element in A that does not satisfy this property, or an element I need to produce an element A which satisfies this property but not this, or this property but not this. So let us try to do this. So let us try to produce an element B that is greater than S. How do I produce an element that is greater than S? I need to just add some positive element. How do I get that element? See, S square is less than 2. This implies what? 2 minus S square is positive. So what, maybe I will write down this as some element delta. So surely this S plus delta is greater than S, right? Delta is positive, I am simply adding some element. So this is satisfy this condition. Now I need to verify, I need to check that v square is less than 2, then this contradicts this condition. So let us check what happens to s plus delta square. S plus delta square, what is this? S square plus 2s delta plus delta square. All I know is that just the first component is less than 2. I do not know about anything about this, it is not very clear whether this is, whether adding this still keep s square less than 2, it is not very clear. And something that bothers me is that there is a, it says we are taking some number, we are multiplying by 2. So suppose this is even if it is less than 1, multiplying by twice might increase this quantity to a large extent, so that this might not happen. So my first problem is that I want to get rid of this 2 here. So how do I get rid of this 2? So instead of taking this lambda, if I take lambda by 2, this will go s plus lambda by 2 square s square plus 2s lambda by 2 plus lambda square by 4. So this 2 is already gone. Now I only have this s lambda, s delta plus delta square by 4. Now I want to get rid of this s also, because s square is less than 2, but s can be positive, s can be greater than 1. Maybe how do I know that? For any element A whose square is less than or equal to 2, s is greater than that element. In particular, for 1 square is 1 is less than or equal to 2, so this s has to be greater than 1. So once I have this s delta, this is slightly bothering me, because this component may be more than what you want to. So I want to get rid of this also. How did I get rid of this 2? I simply multiplied delta by 1 by 2, so there will be 2 here and it gets cancelled. Similarly, I want to get rid of this s. So for that, what I do is, instead of 2, I'll take 2s, s square plus this 2, this s is gone, it is simply delta now, plus delta square by 4s square. One unfortunate thing happened here is s is gone here, but s square is in the denominator now. This is still not very bad situation, because s square is, yes, I said it is greater than or equal to 1. So s square is greater than or equal to 1. So 1 by s square is less than or equal to 1. So having s square in the denominator is actually helping. We are able to get rid of this completely just by using 1 here. So what does it mean? It means this. Right, I can get rid of 1 by s square just by multiplying that with 1. Now there is still some delta square here, delta here, these two are not compatible. Now let us go back and observe what is delta. Delta is 2 minus s square, right? The s is of the form, s is of the property that s square is less than 2, and that s square is greater than 1, right? That is what I said just now. So 1 less than or equal to s square is less than 2. So what can we say about 2 minus s square? This delta is strictly less than 1. So because it is less than 1, this delta square is less than delta. So this will be an exercise. So if I know that an element A is less than 1, this should imply that a square is less than a. You can try this exercise. Because a is positive, I can multiply a on both sides. A dot a is less than a, 1 dot a. A dot a is what? A square is less than a. So in this case, delta square is less than delta. So now I can get rid of this also. So maybe I will write down one more time. So s plus delta by 2s whole square is less than or equal to s square plus delta by 4. I know this first component is less than 2, but this might still be maybe too much for us. You see, maybe if delta by 4 is not there, that would still be fine for us, because what is s square plus let me write down, what is s square plus delta? this is simply 2, right? At some place we have written inequality here, so we can get rid of this actually. So some place we have written, so this s plus delta by 2s whole square, if we can get rid of this delta by 4, we will simply have s square plus delta, that is 2. So what does this say? There is an element s prime that is greater than s whose square is less than 2, that contradicts the property of s. The property of s is what? For any element, if an element is greater than s, that square should be greater than or equal to 2. So this is where we get a contradiction. Now we want to get rid of this delta by 4. How do I do that? If you observe here, delta it was delta square, then multiplying the second component by an element in the denominator decreased this to some extent. We want to decrease it further. So what we will do is we will just, instead of taking 2s, let us take 4s square. So what do we have? This is same thing as s square plus 2s delta by 4s plus delta square by 16s square. Now for the same reasons, this is equality actually. For the same reason I mentioned before, what is this? This is s square plus delta by delta by 2, just delta by 2, 2s is twice, plus delta square by 16s square. For the justification that I mentioned before, s square can be ignored, but I need to write here less than or equal to. Similarly, delta square can be ignored and we can simply write delta, but then this should go, the equality should go, and delta by 16 is, so this is what? So this is equal to s square plus delta by 2 plus delta by 16. Now what were we expecting? We are expecting that we get some just delta here, but here if you really want to get delta, one can do that, because 1 by 16 is less than 1 by 2, so s square plus delta by 2 plus delta by 2. 16 is greater than 2, 1 by 16 is less than 1 by 2, and these two adds up to give just delta. So this is equal to 2. So what did we get? Starting with assumption that s is of the property mentioned before, we got an element s prime, that is s plus delta by 4s, whose square is less than 2. This is a contradiction for the property of s. S was of the following property. If I know that s is, if I know some element is greater than s, that square should be greater than or equal to 2, but here we got the contradiction. So this says s square is less than 2 is not possible. Similarly, one can write down the same thing, s square is greater than 2. So this part will be your assignment, maybe I'll get the next week. So this is also not possible. So this for s square to be equal to 2. So what do we have now? If we are starting with an element that is positive, we are here starting with 2. 2 belongs to R, positive. Then we proved there is an element s belongs to R whose square is 2. This element is what we are calling as root 2. This is the symbol for an element in R whose square is 2. This is root 2. This is the usual root 2 that you already know. Now, what is special about 2 here? One can do the same thing for any element. If I take any element A that is greater than or equal to 0, the same thing. See, 2 is not playing any role here, right? You can see. Maybe you need to change this slightly appropriately depending on what you want, but 2 is not really playing any role, just that it is positive. So one can do the same thing for any arbitrary element A. So then we have what is called root A. So for every R positive, there is an element S belongs to R, such that S square is equal to A. So this says there are square roots of positive elements in R. This still does not say anything about extra elements of, see, this does not really say. It might happen that all root A are actually elements of Q. How do we know that this does not happen? So let us prove that. So let us take this element 2, root 2, suppose root 2 belongs to Q. What is this? Which means what, root 2 is of the form P by Q such that P and Q are co-prime. So here I am assuming that you know some algebra. I should mention about this fundamental theorem of arithmetic and all that, but for now I am assuming that you already know this, and we have this property. So what I do is I will just multiply, I will just take square on the both sides. So this says 2 is equal to P square by Q square. So this is what, P square is equal to 2 times Q square. 2 is an element that divides the right hand side, so it should divide the left hand side also. 2 divides P square. Because 2 is a prime number, this implies that 2 divides P. So what does this mean? This means there is an element K belongs to, because we are asking P to be integer, K is an element in Z, such that P is equal to 2 times K. So we will just substitute this here, and then we get 2 square is 4, so 4K square is equal to 2 times Q square. So this 2 gets cancelled here. So this is what, 2K square is equal to Q square. So 2 divides this left hand side, so it should divide the right hand side also. So what does it give? It gives 2 divides Q square. Again the same justification, because 2 is a prime number, 2 divides Q square should imply 2 divides Q. So this we have a contradiction, that even though we assume that P and Q are co-prime, we got an element 2 which is prime, which is not equal to 1, that divides P and Q. So this says whatever this symbol that whose meaning that we have given just now, it does not satisfy this property. So root 2 is actually an element of R that we put just now, but it is not an element of Q. Such elements, the elements of R which are not elements of Q, are called irrationals. So these are called irrational numbers, and we have proved just now that at least, see, root 2 is an element of R that is not in Q. So there is at least one irrational number. One can do the same thing for any other element, A positive, right. Whatever I have done here, one can do the same thing for A also, but there is a slight problem. We have used that 2 is a prime number, so maybe this might not work for all positive real numbers, but if A is a prime number, there is a large chance that root A is not an element of Q. So we use the 2 is a prime number to some extent. So maybe exercise, if A is a prime number, this might, it is up to you to check, this might imply that root A is not an element of Q. Root A is an element of R, that is for sure, because that is what we have proved in the previous discussion, in the just before we finished some discussion, right. So the same idea, that A square, we collect all elements whose square is less than A, we collect all elements whose square is greater than or equal to A, then the completeness property says there is an element S which satisfy the obvious condition that I mentioned before, that element is the element whose square is equal to A. So root A is element of R, but if A is a prime number, there is a high chance that root A is not an element of irrational numbers. So you can check this for yourself. So now what do we have? Just the completeness property of R suggests there are so many elements in R that are not elements of natural numbers or integers or rational numbers. So, this is where we stop this session. In the next session, we will try to understand more things about this infimum map. So, we have mentioned here, right. We will try to understand what this really means. We need to, we will look for some properties of these maps, and yeah, that's all for this session.